This instructional video will help you find the names or name formulas for binary ionic compounds. This general process is what we know as nomenclature. Now, the root word of nomenclature is the actually German word Namen, which means name. Within nomenclature, there are two systems. There's the ionic system for ionic compounds, and there's the covalent system. Now, with the ionic covalent systems, do not confuse this with bonding. Okay? Ionic bonding, covalent bonding is something different. Nomenclature, you can actually have covalent bonds in a compound, but it end up being an ionic compound in the nomenclature system. So when we're looking at this, we're not looking at electronegativity, we're not concerned about bond type. Whether it's ionic or covalent is determined by what is actually in the compound itself. Now, when we're finding the names of what we're going to call binary ionic compounds, and the root word here, where the word of significance is binary, okay? And we know that the prefix bi means two, so we're talking about compounds that are made out of two elements. No more than two elements. If it's got more than two elements and it's not binary, therefore it falls under something different. Binary compounds are going to have two parts. There's going to be a metal, and then there's going to be a non-metal. When you're naming these things, you simply name the metal, plus you name the non-metal, ending with the suffix IDE. So for example, if I had NaCl, the metal here is sodium, and the metal will always come first. The non-metal here is chlorine. So we use the name of the metal, sodium, and then we use the first part of the name of the non-metal, but we're going to end it with the suffix IDE. So this would be chloride. We wouldn't call it sodium chlorine, it's sodium chloride. Anytime you see "ide" on the end of it, that means it's ionized and it has received a negative charge. It gets that by taking electrons from something else. If it were the element itself, well, then you would use the element name, but when these things are in a compound, you're looking for that second part to end in IDE. Some other examples of naming compounds. I've got three listed on the page. All of these are going to be ionic because your first element is going to be a metal. And generally speaking, that's what you're looking for with binary ionic compounds. You're looking for a metal on the front and then a non-metal on the back. So this being ionic, you name the metal. Mg is magnesium. F2 by itself would be fluorine, but because it's attached to the magnesium, we're not going to call this fluorine. We're going to refer to it as fluoride. CaO, your metal here is calcium. The non-metal is oxygen, so we would call this oxide. Okay? In this case, we have a metal and a non-metal again. The metal here is lithium. The non-metal is hydrogen, so we're going to refer to this as hydride. And like I said, that non-metal on the end of it in a binary ionic compound is always going to end in IDE. I will say that IDE stands for it's an individual darn element. Okay, so if you're hearing that IDE with two exceptions, being cyanide and hydroxide, that means it's going to be a non-metal by itself that's attached to something else. Now, if you're getting the formula from a name, which is going in the opposite direction, okay, so the question is you have a name and you're trying to get the formula from it. There's a process that go through in order to generate the formula. Because if you look back here, you notice that here we had a 2, down here we didn't have anything, down here we didn't have anything. Sometimes you'll have a 3, and the purpose of that is that when you're doing these things, generating these formulas, what we've observed is that they generate formulas in ways so that charges zero each other out. If you end up with a net charge, well then it's not a stable compound, and you haven't honestly generated your formula correctly. The process that you go through this is, number one, we're going to write down the ions. So you go to your periodic table and you look up potassium, which is K. It's in the first column, so it's going to end up with a +1 charge. Phosphide is P, and if you look, it's under the nitrogen column, and by now you should have a -3 written above that column on your periodic table, because everything in that column is going to have a -3. Generally speaking, your first column on the periodic table, your hydrogen column, that's going to be a +1, beryllium's +2. Jump over to boron, that's your +3 column. And hop over to nitrogen, you have a -3, oxygen -2, and the fluorine column is -1. Okay. Step 2, what I'd like you to do is eliminate the signs. In other words, we're just going to cross out these sides. Just go ahead and get rid of them. And the reason why we're doing this is because these things are going to pair up in a way so that your charges, your signs, are going to be eliminated anyways. Number 3, we're going to crisscross the numbers. And what I mean by that is that the 3 is going to come down here, and the 2 is going to come down here. So you're going to end up with a K3 P1. Now, ones in formulas are something we, generally speaking, don't write. It's understood. The fact that you wrote the symbol there at all, in this case being the symbol for phosphorus, means that you're going to have at least one of them. If you've got more than one, well then your subscript down here is going to tell you how many you have of that element. So in this formula I have 3 potassiums and 1 phosphide. And that's how they're going to pair up in order to cancel each other out. So the way we would actually write this is just simply K3P. The second example I have is aluminum sulfide. Well, step number 1, we're going to write down the elements with their charges. Aluminum has a +3 charge. Sulfide has a -2 charge. Step 2, we're going to get rid of the signs. They're just going to go away. And then step 3, we're going to crisscross the charges, so the 2 comes down here, the 3 goes down here. We end up with Al2S3. In other words, to neutralize each other, it takes 2 of the aluminums with the +3, and it takes 3 of the sulfides with the -2 in order to neutralize the charges, because that's what happens with these things. They pair up in a way so that their charges neutralize each other. Now, here's a case you're going to run into sometimes where there's a 4th step, which I'm going to go back over here and write this down for reduce if necessary. And here's what I mean by that. If you look up strontium on the periodic table, it has a charge of +2. Okay? Selenide is going to have a charge of -2. So when you eliminate the signs and crisscross them, you end up with SR2, SE2. When you look at your subscripts, anytime that both subscripts are divisible by the same number, you must reduce them with ionic nomenclature. So both of these are divisible by 2, so you end up with SR1 SC1, which would be written SRSC. Now, just something to chalk up into your memory. You may want to jot this down in your notes. When I started right here, note that the numbers were equal in magnitude of opposite charges. Anytime that's going to happen where you have the same number with opposite signs, you're going to end up with just one of each one. So if you just want to start off, just say, well, they're the same, and just write down the two symbols, that's going to be correct. Another example, this would be something like aluminum nitride. Aluminum, once again, has that +3 charge. Nitrite has a -3 charge. Notice that the numbers are equal in magnitude with opposite charges. So they're +3 and a -3. That tells me right away the formula is just going to be ALN. If you go through the process where you eliminate the signs, crisscross the charges, you end up with Al3N3. Obviously 3 and 3 are both divisible by 3, so you're going to end up there to begin with. So, like I said, when you're looking at these things, when you look at the charges, if they're the same, go ahead and write them down as they are. If they're not, you're going to end up with subscripts at the bottom, and they're going to once again pair up in a way so that the overall charge neutralizes and becomes 0.